So my first lecture today will be about chaos and black holes, and I hope in the next 2 lectures to talk about wormholes and traversability, and so that's the plan of the lectures. Okay, so today we will try to, so the main goal of this lecture is to connect this growth. So when you are near the black hole horizon, if you take a particle from the far future and you extrapolate backwards, it has a large blue shift, and it interacts strongly with particles that were falling in the very beginning. And so there is that effect that we'll try to relate to chaos, and that is the objective of the lecture, so to explain how this relationship works. And as a byproduct, we will also understand the general result for chaotic systems on the development of chaos, which is a so-called bound on chaos. So the main formula that we'll discuss will be the following. I'm going to just write it down, and I will explain through the lecture what the symbols mean. But so this whole lecture will be about trying to understand this formula, that the commutator between 2 simple operators grows with time. So I'll explain the details of what this formula means, but the whole lecture will be about this formula and how it arises from black holes, how it arises in general systems. And most of the ideas that I'm going to be discussing today were in papers by Schenker and Stanford, and there are also some contributions from Kitaev. Okay, so now, so that's the main formula. That's what we will be discussing. But before we start with that, let's discuss a few features about classical chaos. So we'll discuss a bit about chaos, and we start with the classical case first. Okay. So imagine we have the phase space, let's say, of a dynamical system, and which has the dynamics, let's say, takes place in a finite region of phase space. And we have some initial particle, and it follows some trajectory. Okay, so that's simply the time evolution of the initial particle. Let me draw it better. So let's say something like that. Then we change slightly the initial conditions of this particle, just a very small infinitesimal change, and then we'll follow a different classical trajectory. And in a chaotic system, these 2 trajectories will start diverging exponentially, and so there will be, so if we, let's say, change the initial, let's say we start from the same Q position, but we change the momentum, we'll have, so we want to understand how the position what is the relative change in the position between the original trajectory and the new trajectory at time t, right? That will be this distance. As in terms of what we expect that is linearly proportional to the change of the initial, let's say we change the initial momentum at time 0, okay? So then this derivative is equal to the Poisson bracket between Q at time t and Q at time 0, right? So if we compute this Poisson bracket, we'll be taking the derivative with respect to P0, P at 0 of this momentum. Okay? Now this is what happens initially. If you continue evolving these variables, this dynamical system, eventually this exponential growth will stop and will reach the bounded system, and the particle can now will not obey a simple law like this. The relationship between the initial position and the final position and the initial change will start being nonlinear, and we'll get a bit of a mess here, exactly where the particle ends up. Okay. So it's important for our discussion to distinguish this initial development of chaos versus this final story of where the particle ends up, and eventually we expect that these 2 final positions are completely random in a chaotic system, right? The system is ergodic, and we'll get these 2 positions at some random place in phase space. Okay. We'll not be talking about the second thing, about the final complete thermalization or ergodicity of these particles, but only about the initial development. Okay? That's will be our goal. Now, another important point is that if you had a thermal system where this particle could be anywhere, right, and you do an initial change in the positions, you wouldn't notice the difference because it could be anywhere before. You do this initial change, and so, but in some sense, these changes leave the thermal ensemble essentially invariant. You would make a little change, and then the system will thermalize again, and you would not notice these diversions of trajectories. For that, we'll need we need some observable like this that keeps track of where the initial trajectory was and where the final trajectory ends up. Now, so that's classical. Now, then we can discuss quantum chaos. Now, usually, sometimes when you hear people discussing quantum chaos, one of the first things people say is that the Schrödinger equation is linear, and so therefore there is no chaos somehow in quantum mechanics, or at least not in the Schrödinger equation. But that's somehow conceptually wrong. And the reason it's conceptually wrong is that we should compare the Schrödinger equation to, or the evolution of the density matrix, to the evolution of the Liouville equation, the phase space density in classical mechanics. And the equation in classical mechanics for the first phase space probability density is also linear. So the chaos in quantum mechanics is a chaos, if you wish, in the observables, in the same way that here is some property of these functions in phase space. It will be some property of the operators in the theory, the operator algebra. Okay? We'll try to understand what that property is in a second. Yes? Not for the purposes I'm talking about. Yeah, of course, no. I'm just saying that both equations are linear. I'm not saying that they are the same. Of course, the equation for the wave function, right? Then you need to take the square of the wave function, and there are phases in quantum mechanics. I mean, I'm not saying classical mechanics is identical to quantum mechanics, but we should compare properly the concepts in the two areas, right? Yeah. No, well, it's similar. I mean, the fact that there is a symplectic map that is area preserving and so on, and unitarity just things get mapped into. Things get mapped in Hilbert space in a way that preserves inner products and so on. I think this is somewhat similar. And of course, the classical version of a unitary map is one that preserves the volumes, the Poisson brackets, right? Okay, so good. Now, a lot of attention in quantum chaos has been devoted to studying the spectrum. So people say, well, let's look at the spectrum of a system with chaos. And so people notice that if you have a classical system that has chaos, and then you look at the quantum system, then you look at the eigenvalue, at the spectrum of energy eigenvalues, so these are energies. And then for a quantum system, that spectrum is similar to the spectrum of a random matrix. And then in particular, there is some precise law for how the spacing between nearest eigenvalues behaves. Now, so that's for a chaotic system is supposed to have a spectrum of this kind. And if you have an integrable system, on the other hand, you would not have this eigenvalue repulsion characteristic of random matrices. So in random matrices, it's not very likely, or it's suppressed to have eigenvalues which are very close. So the eigenvalues, in some sense, repel each other. And that does not happen in integrable systems. Now, we will be mostly interested in many-body systems, or large-hand systems. Yeah, please.
What would be the parameter which splits the energy levels in the case of the random matrix systems?
Yeah, so you basically, to do this comparison, you have here some mean eigenvalue density, and then you adjust the Gauss, so the random matrix is just the Gaussian matrix, and you adjust the variance so that the densities are equal. The mean densities are equal, and then you can start talking about the eigenvalue spacing and so on. So that's a free parameter. This relationship doesn't say anything about the mean density, it's just a statement about the relative distance between nearby eigenvalues. This is not my point, but I'm just mentioning this because I want to try to contrast with what we are going to study. This is not what we are going to study. And the reason we are not going to study this is that for systems of large n, where the entropy is of order n, then the eigenvalue spacing, so delta E, will be of order e to the minus n, right? Or e to the minus the entropy. So that's the mean spacing between eigenvalues. So this is a very tiny energy, and it involves very long timescales. Okay? So we're going to be interested in shorter timescales. So the timescales we'll be talking about will be timescales that reflect this initial development of chaos. So, and I'm going to say exactly what the timescale is in a second, but the timescale related to the energy eigenvalues is what happens after these two particles, if you wish, have completely separated, and it's a property of the whole system, of the exact energy eigenstates. So we will be interested in a shorter timescale. So, okay, so now let me say what we are going to be interested in. So, we have a many-body system, and so classically we might be interested in analyzing how qi of t and q, let's say, j of 0, so we have two different, let's say, particles, and we might be interested in how this commutator grows. That reflects what happens under a small change. Of course, this commutator could grow, and it could have either sign. It could be positive or negative. And we could start from different initial points, right? And this could grow differently. So what we're going to be interested in is in taking an average of this over the thermal ensemble. So it's just to get an idea of the average growth. But because this could be positive or negative, it's not a good idea to just average this quantity. It's better to take the square and then average. Okay? So we could take the square and then average over the thermal ensemble. So that's something we could do in the classical system. And that we expect that for relative short times, this will grow like e to the lambda t, where lambda is, by definition, what we will call a Lyapunov exponent. Sometimes this one here, when this grows like e to the lambda t, is called the Lyapunov exponent. There is a factor of 2 difference between these two definitions, but we're going to take this as our definition. Yes? It was because if we're going to do a thermal average, if we don't square, there might be just some cancellations, because some places could be positive and some regions it could be negative. So then the quantum version will be essentially the same, where we take 2 operators. So one will be evolved in time, and the other one will be, let's say, at time equal to 0. And then we take the square of the commutator. So now this will be a positive, well, actually it's a negative operator, but a definite sign. So maybe we can do minus that. Again, the average over the thermal ensemble. So trace of this e to the minus beta h. Okay? And that, we expect this to go like 1 over n. So it will be, we are imagining it's a large n system, and that these two are 2 simple elementary operators. So a good picture for this is to think that we have, let's say, a spin system or one of these system with Majorana fermions, and so it's good to think about this as a simple operator. It could be like a sigma matrix. Okay. So this operator could be a sigma matrix that acts on one of the spin degrees of freedom, and this would start at equal to 0 being a sigma matrix, but then we evolve with the Hamiltonian. Okay, that simple operator.
So in the classical case,
Yes.
lambda doesn't depend on beta, right? Any state that you put depends on the maximal eigenvalue there.
Yes, well, it could depend on beta because for larger betas, you explore a bigger region of the phase space, right? And the system could be evolving faster if, or differently with bigger energy.
Degrees of freedom in general is not, right?
What?
For few degrees of freedom.
Well, even for few degrees of freedom, well, let's imagine the microcanonical ensemble first. You have some energy, and then as you raise the energy, you could have a different, well, you have a faster evolution. So here, the idea is that, yeah, when you raise the energy, you'll have faster evolution, and you might have a faster lambda. Well, we'll see that later, but you expect just intuitively that as you increase the temperature, the whole evolution will be faster. As you cool it down, everything gets lower, and including this lambda, we expect it to be smaller. Yes?
Is this connected to Kolmogorov-Sinai entropy? You just take beta to infinity or is there a connection?
I think there is a connection, but I don't know it. Yeah, classically, I think the Kolmogorov-Sinai entropy is a relationship. There is a relationship between Kolmogorov-Sinai and the sum of Lyapunov exponents, classically.
But this is a single number for the entire phase.
Yeah. Okay. So we are going to, so just to have a picture, or well, not to have a picture, but the kinds of systems, I'm going to say a little bit more about the kinds of systems we are going to consider. Okay? So we'll have in mind some system that contains some simple degrees of freedom, which we can think of as spins, let's say Si, or we could think of them as Majorana fermions, Sj, Sk, right? So simple elementary degrees of freedom. And then we'll have a Hamiltonian, which is called K-local, which is the definition of K-local is that is the sum of terms, each term involves a few of these spins at a time. So there are some coefficients, let's say I, J, K, and then S, I, S, J, S, K. So these are sigma matrices. Of course, there could be the indices of the sigma matrices, alpha, beta, gamma. These indices go from 1 to 3. And then this I, J, K go over all the spin degrees of freedom in the system. Okay. So here I put 3, but so here K would be 3. But well, the idea is that K is a finite thing. So we have a huge number of spins, but the Hamiltonian only takes a few of them at a time. Okay. That's the definition. Now, there are many systems that have this property. So examples could be, simple example would be a spin chain. So imagine all the spins are arranged along the chain, and that the Hamiltonian is local in space. Then the Hamiltonian is a sum of terms like that, and here of neighboring terms. So K-locality is a property that generalizes the notion of spatial locality. Okay? So for example, another example is a matrix model, so a matrix theory, where your fields are arranged into matrices that have, let's say, 2 indices that go from 1 to n, and then you have interactions that, for example, are of the form, so commutators between 2 matrices, x and y, square. I mean, this is just one example. I'm just writing this because this is the type of structure we get in large n-gauge theories. Even a matrix quantum mechanical model also is K-local because you only affect, so this is a sum of terms. I mean, this will involve 4 matrix elements at a time, this Hamiltonian. Okay? And it's a sum of terms like that. So matrix models are an example of this. Yes.
To your spin system,
Yeah, non-K local would be something which, for example, would involve n over 2 spins. So let's say you have a term that involves all n spins, for example. Let's say some term in the Hamiltonian involves all spins at the same time. Then that would not be K-local. So that's an example. So it's not that all Hamiltonians are K-local, it's just that all the ones for which the discussion we're going to have applies are K-local. But these are all the Hamiltonians we normally encounter in systems that we apply, well, we are usually discussing in this conference. So examples are spin chains, so chains, or local quantum field theory. It's another example. We could take a local quantum field theory. Well, I guess usually the definition of quantum field theory includes that it's local. We can always discretize it in terms of some basic spin degrees of freedom, and then we construct it in that way that we will obey this definition. Of course, the SYK model that we heard from Kitayo is also an example of a theory like this, with no particular spatial locality. Tensor models and so on are also of this form. Okay, so so in these models, so the Hamiltonian is a sum of many terms, but each term is relatively small, and so these models tend to have a 1 over n expansion. That if you have two different degrees of freedom, two simple operators, their correlators can be organized in a 1 over n expansion. In particular, we expect that this commutator, again, will be of order 1 over n. I'm going to try to explain, let's say first, let me try to explain why that is the case. So B will always be the one that is at t, and W, let's say it's at 0. So we expect that this commutator will be of order 1 over n. Now, because, so let's get a picture for this commutator. So let's imagine that W of 0 acts on one of the spins, and let's start with the operator V at t equal to 0. So that will act on some other spin. So let's say the spin number 1. And then when we act with the Hamiltonian, we have to commute the Hamiltonian with that spin, right? So all we are doing here is the next term. So this is the first term that would be V of 0. And then I'm going to write here the commutator of H with V of 0. And that will generate a few spins, right? So we can draw it like this. So these are the spins, let's say I, J, K, that would be generated by one of the terms in this Hamiltonian. Okay, that generates, well, in this case, yeah. So it anti-commutes, let's say, commutes with this guy, gives another spin here, and then we have the other two spins. And then we act again. So that's this term, and then we act again with the Hamiltonian H, commutator H, V of 0, right? So we're building the V of t as a series expansion. So if this is t, then this is a term of order t squared, and so on. And then each time, so now when the Hamiltonian acts here, it will connect to other spins in the system, okay? And in this case, and we start getting a picture that looks like this, where we have a kind of branching tree, where the first, where initially V involved only one of the spins, but then as we do this evolution, it involves more of the spins of the system, okay? So if we were to ask what's the probability that, let's say after one step, one of these spins would be the spin corresponding to W. Let's say W is spin number 2, okay? And this was spin number 1. Then it's small, it's like 1 over n. Let's say that will be the second one. And but then as we start moving, of course the probability that the spin 2 is one of these for each individual one is small. But since we have many of them, the probability that it is one of them will start growing exponentially. Okay? So the exponential growth is related to the fact that the number of legs in this tree is growing exponentially. Okay? So then, when we take the commutator with the second operator, it's highly probable that it will have a non-trivial commutator. I mean, this type of structure, well, appears well in this type of problems. Also, is similar to the structure that appears, for example, when you have a shower in, let's say, QCD, that you have a gluon that splits into other gluons and so on. It would actually be nice to connect those two pictures more explicitly. Okay, so that's the picture, and just based on this picture, we expect that the commutator will have time behaviors as a function of, so this is the commutator, so this is this quantity here, and as a function of time, well, let's say the commutator should start out being 0, and of order 1 over n, so very small, but so a small prefactor, but growing exponentially, so it grows exponentially, and eventually, after a time of order the logarithm, so 1 over lambda times the logarithm of n, after this time it reaches a value. After this time it reaches a value of order 1, and then it approaches typical value, which is roughly some number of order 1. So what is this value of order 1? So it's saying that this operator became so long, so complicated. So the idea is that initially the operator is just a single spin. And then as time evolves, the operator becomes sums of products of different spins. Okay? And by a very long time, the operator will be sums of products of essentially all spins. And so it will always include the spin W. Okay? And always the commutator will be just the commutator of 2 sigma matrices, which is something of order 1. Yes?
That time in which the probability of finding the
Yeah.
operator is of order 1
Yes.
is not the same time which the operator is composed by, let's say, n spins. No?
Yeah, that's the idea. That is when it reaches all n spins.
But it's clearly not the same, no? Because to reach n spins, you have to, if it's k local, you
Yeah.
have to apply the Hamiltonian n divided by k times. So the question, so they are two different questions, no? This is a doubt that I have for a long time, but I think that they are two different questions. So one question is the one you posed, which is when the probability of finding your reference spin is of order 1 in the
Right.
which is that time. Another one is when the operator is constructed from a chain of n spins, which has to be n divided by k.
Yeah, you're right. You're right. Yeah.
Okay.
Yeah. Yeah. Yes.
When you apply the k-local Hamiltonian, there are commuting terms which are working at the same time. So it's not naively, it's not just n over k.
Well, yeah, in this tree, I guess here the number of legs in the tree is growing exponentially, right? So it's just this. Yeah, so.
To reach a size n, you don't need an n over k time.
Exactly. That's the point. It's a difference.
But I was saying the time you can get size n can be log n because the size grows exponentially, even if k-local.
Let me answer that question better next time. Okay, so this behavior, I would like to contrast this behavior with the behavior you would have in an integrable case. So imagine you have something like a single spin that is moving along a chain, right? So in that case, what happens under time evolution is that the spin moves location, right? So a single spin becomes a superposition of spins at different locations, but it's always one spin. It's not growing into a product of different spins. So in that case, what happens is that in that case, what happens is that you take the spin I, and after at time t, right, it will be some matrix that depends on time of the sum of all the other spins j. Okay, but it involves only one spin at a time, right? Not all spins at the same time. Okay.
Sorry, lambda depends just on the Hamiltonian or also on the particular choice of the operator?
Yeah, lambda could depend on the choice of operator, but the idea is that in a sufficiently chaotic system, it will be a universal thing. There could be, in principle, superposition of different lambdas. We are talking about the maximal one. And in a sufficiently chaotic system, we expect that it should be independent of the operator. But in fact, there are some integrable systems where, depending on the operator you take, you might have a behavior like this. Sometimes they don't grow, sometimes they grow with some lambda. So a chaotic system would be one in which any operator should grow in this fashion. Okay, so now let me say again the comment that I was making before, which is if we have a system. If we have a thermal system and we do some perturbation, let's say let's say epsilon W of 0, so that's a perturbation we do on the thermal system, and then we measure V of t. This will also include some commutators, but this is the type of thing that we don't expect to grow. So this is a perturbation to the system, to the thermal system, and we expect that this perturbation decays. Okay, and this type of correlator is what is within what we can call time ordered. I mean, it's at least time ordered on the Schrödinger-Keldysh contour, and it's the kind of thing that we can measure easily. So we can take a system, we do a small perturbation, and then we measure something at time t, and we expect that the effects of the perturbation will decrease. So we had this initial picture, so that classical picture where we think that when we do a perturbation, we perturb the trajectories and they differ from the previous one, but because we are doing the thermal system, we cannot distinguish that perturbation. So we really need to do this commutator, and that involves a more complex correlator, as I will try to explain now. So we can take that commutator, V of t, W of 0, and we can expand the various terms in the commutator. So one of the terms would be let me see, W of 0, W of 0, V of t, W of 0. Okay, so that's one of the terms of the commutators. Then we get with the minus sign, we'll get, well, the same here, V of t, W of 0, but we get these two in a different order, W of 0, V of t. Okay? And then we get two others, which are a simple permutation of these two. Now, here we see that we get we can view the other two as the Hermitian. Yeah, so the other two are simpler. So here we can think of this as a perturbation at 0. Then we calculate this 2-point function at time t. And then we get, again, the perturbation at 0. So this is what we can call a time order correlator. It's something we can, in principle, measure easily. Okay? While this one here is a more complicated object, here we measure something at time 0. Then we measure something else at time t. Then we have to evolve the system all the way back to time 0 to measure this one, and then all the way back to time t. Okay? So if we imagine the type of contour that we need for this, so we start at time 0 where we insert w. Then we go forwards in time. We do something at time t. We measure v at time t. Then we go backwards in time. We measure something at time 0 again. And then back forward in time to measure something at time t, and then if you wish back here, and then we are computing in the thermal ensemble, so we go along Euclidean time. So you need a more complicated contour like this, which is, has one more back and forth in time than the usual, let's say, Schwinger-Keldysh contour, which are the type of contours we get when we want to compute some physical observable in the theory. So doing this type of experiments, if we would like to do an experiment of this kind, we would have to somehow evolve the system forwards in time and then change, arrange for some way of changing the sign of the Hamiltonian and evolving the system backwards in time. Now, some people have been studying this, in particular here Horacio Postaski has been studying this with NMR systems, of trying systems of spins, of evolving them forwards in time, and then by some NMR technology you can invert the sign of the relevant terms in the Hamiltonian and evolve it backwards in time and try to doing computations in this way. So this is something you can do in some systems. You can do this backwards and forward time evolution. Yeah, and so people are trying to design other experiments. So I guess Brian also has been thinking about experiments you could design to measure this effect, in particular to measure this initial growth of the commutator. Now, so at time equal to 0, so this 2-point function, let me discuss first this order correlator. So here, we can imagine the two W's here and the two V's at late times. So here we have something which is like a spin-spin correlator. So we said that when we do a perturbation at time 0, the system, we expect it to essentially thermalize. So this VV correlator here in the middle, we expect it to be essentially the VV correlator in the thermal system. So that's some number, or you can more or less conceptually think of this as there is the identity contribution in the operator product here that will be the only one that will be relevant. And so we'll get a structure for this one to lead in order. It will be the VV times the WW correlator. And so that's the structure of this one. Okay, good. So this is this one. And at t equal to 0, at small times, we can commute these two, and this one will also give us essentially the same result. Okay, will give us exactly the same result. And so initially, these two are canceling. So this one is 0 because of the cancellation between the ordinary time correlator versus the out-of-time order correlator. So if we just plot the out-of-time order correlator, so by out-of-time order correlator I mean this correlator here, we expect that that correlator starts, let's say, being, let me call it 1, but by 1 I mean this product, okay? So we could divide by that product, and that's what we're calling 1. And it will be 1, and if we ignore any 1 over n corrections, it will be 1 forever, but including the 1 over n corrections, we'll have this exponential decrease of the correlator by this Lyapunov exponent, and then eventually go back down to 0 after a time of order logarithm of n. Okay, so this is again time. So this is essentially the same picture that we drew here, but we are focusing on the particular correlator that is responsible for the growth of the commutator. So growth of commutator is equivalent to the decrease of the out-of-time order correlator. Okay. So here we're just rephrasing things. We're not doing anything, anything non-trivial. So this initial time decrease is this exponential e to the lambda t times 1 over n. So this correlator is expected to behave like 1 minus some number times 1 over n times e to the lambda t initially, and then eventually it will settle down to 0. Okay, so now why do we expect it to settle down to 0? So we can think of this correlator as the inner product between two states. So this is some state number 1, let's say psi 1, and this is a second state, which is the state, the bra of the state psi 2, where psi 2 and psi 1 are the same, except that the order of V and W is the opposite. Okay? So this is the overlap between these two states, and so this going to 0 is just saying that these two states are becoming orthogonal. Right? So initially they were aligned, and then as time evolves, you typically get them to be orthogonal. It's the generic situation. Okay. So now what we're going to do is we are going to calculate this in a system that has a gravity dual. Okay, so now we are going to calculate this in systems which have a gravity dual. So first, we are going to draw here a picture of V of t. So let's consider the state V of t acting on the vacuum. By the vacuum, I mean the thermal field double. So we can imagine that it's the thermal field double, or it's V of t acting on the thermal state. Okay. So we are going to be focusing on the region outside the horizon. So we have a horizon. And then we have a V which we act at time t. So this is time t. And then we'll create, let's say, the operator V will create a particle moving towards the horizon and falling into the horizon. But we're going to be viewing this as a state. And we can evolve this state backwards and forwards in time. And if we evolve it backwards in time, the evolution of the state backwards in time contains a particle that goes now towards the boundary and then bounces back from the boundary. So we're viewing this as a state of the original system. So we have the state, this state evolving with the original Hamiltonian has a dual which corresponds to a particle going to the boundary and then bouncing back from the boundary into the horizon. Okay. Okay, so that's one of the states. So here the key for what I'm going to say is to understand clearly what the states are. So the second state will be W of 0 acting again on the vacuum or the thermal state. And this state, so this is time 0. And again, we can imagine W creating a particle, but then we'll go that backwards in time, and we then get the full state contains a particle coming out of the horizon and then falling into the horizon again. Okay? So these are two states. And now that we have these two states, we can construct, add the second particle. Well, you have to remember this formula, that the out-of-time order is the overlap between two states. Okay? I'm going to erase it, but that's where we are going to. We are going to try to calculate the out-of-time order correlator, and we're going to do that by constructing very explicitly the two states whose overlap we are doing. Okay. Okay. So the next state we are going to construct will involve W of 0, V of t. Okay. 0. Okay. Okay, let me see. I think yeah. So okay, so here we had some state. Let me see. We had written it in pink. So we had some state that was V of t. So it was this state, okay, that contains some particle coming in from the past horizon. Okay. And now we are acting with the operator W of 0. So we act with the operator here, W of 0, and we create a particle coming in here. Okay? So then these two particles will interact, and in the future they will create something that will result from these interactions. But at this early time, this is the picture for the state V of t, W of 0. Okay? So we can have a simple picture for it in this initial state, as an initial state. Then what will happen in the future depends on what happens in this interaction. If we make the approximation that they don't interact, they just go through each other. Or if they interact, then something new will happen. So then, now here we'll have the state V of t, W of 0. So here we so we had initially the state. so V of t was creating something here, right? And so here we get a simple description for the final state. So we have some final state. Well, initially we had this, this V of 0 here, and when we create the V of t here, we can evolve this one backwards in time. And as we evolve backwards in time, really what we care about was the initial condition, well, the final condition, if you wish, that we had for W of 0. And then when we evolve backwards in time, we can evolve it backwards in time up to this time. And then from here onwards, we will need to take into account this interaction. Okay? So, so this one can be obtained simply by this backward time evolution, this one by this forward time evolution. And so this is the region in space-time where we know clearly what the states are, ignoring the interaction. Okay? And so now we are interested in computing the out-of-time order correlator, which was the overlap between those two states. Okay? The two states here on the blackboard. So we call this this state psi 1. I'm not sure if this was consistent with my previous notation, but and this state psi 2. Okay, no more color chalk, I guess. The color chalk cannot be seen as easily. Is that true? Or? So now we compute the out-of-time order correlator, which is the overlap between the state psi 2 and psi 1. So this is the out-of-time order correlator. And this, the picture for this is the space-time picture is simply to compute the scattering amplitude between these two particles. So we have some initial state, something goes on here, and then we have this final state, right? That's so this out-of-time order correlator is essentially the scattering amplitude for these 4 wave packets. Okay, so we can think of each operator as creating some kind of wave packet, and we need the actual physical scattering amplitude for those wave packets. Okay, so that discussion showed that the out-of-time order correlator can be computed as scattering amplitude in the near horizon geometry. Okay. So people had previously talked about this type of scattering amplitudes, but so for example Toft and Ray, but it was well, or even after the Hawking calculation, people noticed that there would be a large interaction between the incoming and outgoing particles, but it wasn't clear what physical process or what calculation we needed to do in order to see these scattering amplitudes, because part of the particles are lost behind the black hole horizon. But this out-of-time order correlator is a concrete way in which we can explore this scattering amplitude. Okay, good. Now, we have 1 over n expansion, which in gravity is an expansion in powers of g Newton. Okay, so this correlator, this out-of-time order correlator, to leading order in g Newton is just going to be 1. Okay, it's just these 2 wave packets will simply pass through each other, and we just get 1. And then there will be g Newton corrections to this, so some g Newton corrections. And we'll try to understand what the form, or g Newton, or equal to 1 over n, and we are trying to understand what these corrections look like. Okay. Okay. Now, in particular, we want to understand the time dependence of these corrections. Now, what happens as we make time bigger? So what is the main thing that will happen as we, so this was time equal to 0, this was time equal to t, or well, I guess we could draw them here. Time equal to 0 and time equal to t. As we make time bigger, this, well, one thing is these particles get closer to the horizon, but most importantly, the time evolution near the boundary, near the horizon, becomes a boost evolution. So it becomes evolution under a boost. So that means that as we make time bigger, the relative boost between these 2 particles, or between these 2 particles, grows and becomes bigger. Okay. So the center of mass energy between these 2 particles, S, will start growing like e to the t, okay, e to the boost angle. T is that's for temperature equal to 2 pi. When we put in the factors of temperature, we get that S grows like e to the 2 pi t over beta. Okay. So that's how the center of mass energy, so S is the center of mass energy for this collision, so it's the momentum of this plus the momentum of this squared, grows in this particular way. Okay, so okay, so that's how it goes. So the main feature is that this center of mass energy is growing, and so in order to find the biggest term here, we have to understand which are the contributions to the scattering amplitude that grow fastest with energy. Yes?
At which moment did you begin to worry about temperature in this calculation?
Well, at the beginning. The whole discussion is about what happens at finite temperature. Yeah, sorry, maybe I should have emphasized that a bit more. So we are interested in a thermal system. We always talked about these commutators taking an average over the thermal ensemble. Of course, yeah, you could compute the out-of-time order correlator at 0 temperature and might have some other properties. Well, it depends on the system, but these universal properties we are going to talk about are, well, this whole calculation, this whole discussion is when we have the black hole phase, when we we have a system whose dual is a black hole. Yes?
So maybe you want to answer this later, but
Yeah.
in the old times, Hertog would say
Yes.
this effect allowed to extract information after a time for longest.
Yes, yes. I think those, those are ideas that he only understood. I never found someone who could explain it to me, not even him. And I think the way to think about this is that this is the correct, I view this as the correct version of those calculations. There are some gravity calculations that involve those scattering amplitudes, and this is the correct physical interpretation of those calculations. That's why I went really slowly through here, and hopefully this has been completely crystal clear to everyone. Or, yeah.
But this doesn't allow you to extract information from a black hole.
It doesn't allow me, I don't know. And it's important that we are talking about short times. And this effect is even present in cases where you don't expect to extract information. So for example, imagine you have an infinite black string, right? So that's a system that in principle can lose information because the string is infinite and has an infinite entropy. There is no reason why you should get information back, but this effect is still there. So the fact that if you send localized excitations there could be an infinite black string with the other direction growing perpendicular to the blackboard, and this effect is still there, still present. Yeah, so these are two different things. So this effect has to do with the initial development of chaos, getting information back. It has something to do with much longer timescales, which see the discreteness of the spectrum and all those features. Alexei said this in his talk also, that there were 3 different timescales. Short timescale of order beta, then timescale of order log n, which is involved in all these effects, and then the timescale, which is exponential in n, which is the one where we start seeing some effects of information, at least in a system like this where you are in ADS. So you start seeing some effects of the finiteness of the entropy in simple operator correlators. Of course, if you consider correlators of n particles, then you could start seeing these effects after a time of order s, when you start being able to measure s particles. Okay, so right now, so how does energy increase in scattering amplitudes? So we are going to start. So let's consider simply. So we're going to look at an effect of order G Newton, or the leading effect. That's a simple diagram where we have the 2 particles going in, and they exchange, let's say, some other particle. Okay. And then it turns out that the relativistic amplitude, so the A relativistic in relativistic notation, it goes like s to the power j, where that's how it grows with energy, where j is the spin of this particle. Okay? So if we had, for example, a 5/4 scalar interaction, it's like exchanging a part, or let's say an exchange of a Higgs field, we'll get j equal to 0. If we exchange a photon, we get j equal to 1. If we exchange a graviton, we get j equal to 2. So we see that gravity gives us the highest the highest contribution, so gravity will be the dominant effect at these larger energies. Now it turns out that the physical scattering amplitude we wrote there is due to some kinematic factors, is really this A in relativistic notation divided by S, and so really grows like S to the J minus 1. Okay. Relativistic, it's just the usual relativistic formulas that we get for Feynman diagrams. Okay, so this is the Feynman diagram answer, and this is more like the phase shift of this scattering. So once you put in the wave packets and the kinematic factors and proper normalizations, you get this. Okay, so in the end of the day, then for gravity, we can do the calculation, and we get that the OTC, OTOC, out of time order correlator, goes like 1 plus something like I over N or over N or G Newton here. So this could be G Newton. E to the 2 pi T over beta. Okay. So it scales like S, and something scaling like S, due to that relationship, it scales in that particular way. Okay. So the calculation had a few steps, but they are all simple. So the first thing we did was to understand well the initial and final states. So think of this as the initial and final state. View the process as an amplitude. Notice that for large times, this is happening close to the black hole horizon, and that time evolution acts as a boost. And then we just had to understand which amplitudes grow fastest with energies. The fastest is the graviton exchange, and then it goes like so for gravity, it goes like a single power of S, and that's what we wrote over here. Okay? So in this way, so now the final thing is that we understood how the OTC is growing or decreasing. So in this case, so here we can say that this exponential increase, so e to the lambda, so here we conclude from here that lambda is equal to 2 pi over beta, or equal to 2 pi T temperature, and if we put the h bar, there would be an h bar here. Okay, so that's what happens for black holes. So, yes.
Speak about your gravity field.
Yes. Yes.
Process. You're doing this correlation with dimensional function with W.
Yes.
W and D.
Yes.
You're comparing it with this 4-point amplitude, something like this. You do it according to a dictionary.
Mm-hmm.
Why did you do this relativistic amplitude?
So we have a collision of particles in nearly flat space, right? The near horizon geometry, and we just use the flat space scattering amplitudes. We approximated that by flat space, and the only thing that we used about black holes is that the initial and final state are boosted more and more as time evolves, as you make them more separated in time. Well, this is the out-of-time order correlator, right? We went through this thing just to show that the overlap between these two states is the out-of-time order correlator. And the commutator is the difference between the time order thing and the out-of-time order thing. And we said that the growth of the commutator has to do with the decrease of the out-of-time order correlator. Okay. Yes? Yes, yes. Okay, very good question. So that's what I was trying to say next. Now let's try to do this in string theory. Now the first, so if we try to do it in string theory, we might be a little confused. Because in string theory, the strings, we could exchange many strings with different spins, and we'll get contributions which involve the amplitude the relativistic amplitude divided by S. We get all these contributions that are sum over spins with various spins. Now, So this sum is not really convergent in the, well, first of all, if you naively try to do this sum, it's not convergent in this region. But you can take the full string amplitude and see how the full string amplitude really behaves. And the full string amplitude in flat space behaves like s to the power, well, this divided by, after we divide by s, plus alpha prime t. Okay, so s and t are the Mandelstam variables of the, so we are scattering, we are computing the string scattering where s is the Mandelstam variable of these two, and then t is the one, well, it's the difference, it's the sum of these two momenta, okay, the usual momentum transfer. So t, in this process, t is relatively small, and s is very large, okay? So that's the regime, so that's the string amplitude when s is much bigger than t, and t is, well, t also can be anything. So this is sometimes called the Regge behavior, so how it behaves in the, this is called the Regge region, so s much bigger than all other things, and that's essentially how it behaves. We are a little more careful, there is a minus I here. We want to get the phase right. I'm not going to try to explain that. So this is just comes simply from taking the Veneziano or Virasoro-Shapiro amplitude, so the standard expression with gamma functions, and then taking s very large. Now, what we see is that in the regime that this can be small, so alpha prime is the inverse string tension. So when we are doing this in the gravity approximation, this is close to 0 and does not contribute. In the physical region, t is less than 0. So the sum of these two momenta is space-like. So this momentum is space-like. And so this quantity is less than 0. And we get something which is smaller than 1. So the effect of string theory, naively you might think that the effect of string theory is enhancing, making it larger, because there are all these particles of higher spin. But it turns out that the sum of all these things ends up being, conceptually, roughly the sum of all these things ends up being something which is actually less than the gravity amplitude. So the things in string theory will grow less than in gravity. Okay, so now you can ask, if you have a black hole in string theory, how does the previous calculation get modified? Okay, and the idea is that due to the fact that that whole process is occurring in a background with some curvature, some radius of curvature, the graviton will that we are exchanging will have some net transverse momentum, just basically because we have to somehow localize it within a region of order the radius of curvature. That's roughly the idea. So the idea is that this, doing it, you can do this more carefully than what I'm explaining, but I'm just trying to give you an idea for why we get this answer. So this goes like 1 minus ls squared over some typical radius of curvature. Some radius which you can view it as the radius of curvature of this black hole and so on. There are some exceptions to this. One interesting exception is the case of ADS2 space, or a black hole, near extreme black hole. This is not the radius of ADS, but there's an extra suppression factor that makes this correction even smaller. But this is not too important for now. So what's important now is that that we see that this correction is smaller if we have finite string tension. So that's one point. The second point is that we could calculate this, we can think about this Lyapunov exponent also in almost free theories. So imagine we have a theory which is very weakly coupled. And if the theory is weakly coupled, then all those terms in the Hamiltonian are going to be small. And as we evolve, we expect that the Lyapunov exponent should be small, should be of order the coupling, right? Yes?
So before maybe you go decoupling, can I ask?
Yes.
So in this string theory picture, how do you see the decay at large time?
Yeah, I didn't discuss the decay. Yeah, so let's discuss this. Yeah, good. Yeah, so So we can understand the decay in the following way. So this is a separate question. So here we discuss the initial increase. Okay. So to discuss the decay, we need to say a few more things. So this gravity amplitude, which is a phase shift which is linear in S, corresponds to a picture where when you go through, where one particle goes through the other, one suffers some kind of time delay. So we can draw a picture like this, or we can view the time delay as occurring on the other particle. So this is the situation when. So let's view this particle as some heavy thing that we send, and then we send this as a probe. This one suffers a time delay. So it comes out later than it would have come if we didn't have the interaction. Okay. Now, when we are at very late times, so at very early times, this is a small effect. Okay. But this is the effect we are considering. It's just the tiny time delay, and that's this first correction. Okay. This is a phase shift. This is the first expansion in some kind of phase shift, which goes like G Newton, let's say P plus, P minus. So these are the P plus is the momentum of. Okay, I always need to think about the plus and minus. So this is x plus, and this is x minus. So this particle has very large P minus, and this particle has very large P plus. Okay. So this P plus and P minus do not refer to the same particle, but to two different particles. Okay. The two particles that are having the collision, and so if we fix the, let's say, P plus of this particle, then we see that, so this is, let's say, fixed. We go to some kind of Lycon gauge where this P plus is fixed. Then what we see is that we have a shift in the, let's see. Yeah, we have a shift in the, so this whole thing, so the P minus of the other particle will also be fixed, and we have a shift that goes like e to the I. So we can write this as e to the P plus. We're trying to find the effect on the P plus particle. Some x plus, where x plus is, or delta x plus, is the other G Newton times P tilde minus, right? So that's the shift that this particle experiences. And the sign is such that it's a delay. Okay. Now, so if this is large, we have this shift, but we are computing the amplitude. So the amplitude involves the probability that the outgoing particle comes out here. Okay. So the most probable thing is that it comes out later. We're asking what's the probability that it comes without any delay, and that will be small. Will be decreasing, right? Will become very small. Okay. Now, naively, if you take this picture as face value, it just became 0. Okay. So after some time, it will become very close to 0 very quickly. But what can happen is that when you send these particles, there is so when we send one of these particles into a black hole, there is a whole tail. So imagine we send first one particle into the black hole. So when we send one particle into the black hole, after some time, there is still some probability that the particle hasn't fallen into the black hole. It's characterized by the quasi-normal mode frequency, the lowest quasi-normal mode frequency. And so there is some probability that the particle really wasn't localized here, but it actually, at the time t that we are doing this experiment, it hasn't completely fallen into the black hole. Okay? And the probability that happens goes like e to the minus quasi-normal mode frequency times time. So we expect that and this will be given the leading contribution, because if it was very localized, we would have this big shift. It will give essentially 0. But there is this tail that is governed by the quasi-normal mode frequency, and that tail is important for giving some contribution which is not highly suppressed, and so that's what governs the decay at late times of the OTC. So the out-of-time order correlator has a form where so we have it starts like 1. There is this exponential decay going. Becoming lower than 1, and then here we approach 0 with some quasi-normal mode frequency terms. Okay. Okay. So that's yeah, that answers your question.
This corresponding to summing.
Yeah, and this is the same in string theory or yeah, we expect it to be the same in gravity or string theory.
Right, so this corresponding to summing infinite number of string key exchange?
No, this corresponds to taking more into account the geometry of the black hole, right? And so the quasi-normal mode frequencies have to do not with the near horizon geometry, which is what we discussed so far, but also the further aspects of the geometry, right? It's just saying that this particle didn't follow this naive trajectory and it's not localized at this, along this line that we drew, but has some probability of lingering into
Right,
the
that's
near.
fine, but from the perspective you were explaining earlier.
Yeah, this discussion here was a discussion where we still think of the process as occurring in flat space.
Yeah, so why at the time scale of the scrambling time when the curvature becomes important?
Yeah. So what happens is that when this time shift becomes very large, right, the probability of this process becomes very small. So this is no longer the dominant part of the amplitude. We have to think about some other improbable things, right? I mean, when you're computing something and it becomes very improbable, you have to worry about other improbable things, right? So
This is another saddle point. Just like,
it's not another saddle point. I mean, it's just the tail of the wave function. Before we thought of the wave packet as concentrated here, but it has a tail, and so you can think of the scattering as a superposition of the scattering, well, along the center of the wave packet, which is very small, and then along the tail of the wave packets. But in the tail is extended in the has a piece which lingers at late times, and those pieces that lingers at late time are not so highly boosted. When they eventually fall into the black hole, they are not so highly boosted, and they give a bigger contribution. So it's like a wave packet issue. Not, okay, so what we have seen is that, okay, now when we go to weak coupling, we expect lambda to be very small. And so we see that as we increase the string tension, we go from gravity result to something that goes into the direction of weak coupling, so making lambda smaller. Okay. Now, let's ask the following question. Let's forget about this whole discussion of chaos for a second and think about scattering amplitudes in flat space, right? Why is it that the string scattering amplitude had a total power of S which was less than 1? Okay? And the idea is that, so we have perturbative amplitudes in flat space. Yeah. Yeah. So it's just this translation between the time in the near horizon region and the time at infinity. Right? So in the near horizon region, in the natural units of time where time is measured, units of the temperature, the effect is always the same. It's just. Yeah, so from the many body system, the idea is that the typical term in the Hamiltonian that is activated, right, is of order the temperature. So the Hamiltonian has many other states at high temperature, but I mean, or higher energies, but the system never explores those states. Yeah, it's smaller, and well, things slow down as you go down in temperature. That's the intuition. Okay, so let's discuss just scattering amplitudes in flat space, and let's ask how fast can they grow with S. So the idea is that when you think about high energy scattering amplitude, you can go to this large momentum picture where the particles carry, one of the particles carries very large P plus and the other one very large P minus. And so from the point of view of, let's say, this particle, this looks like something localized here along the x minus direction. Along the x minus direction. And when this particle goes through here, we can think of this as a kind of signal transmission problem in the where we have some wave function which contains some p minus. Well, let me see. Let me get the p pluses and minus. So this is x plus. So this is localized in x plus. So this is some particle that contains some p plus, and we'll have some shift in the x plus direction, right? So we can think of this as a transmission problem where, let's say, x plus is time, and we had, let's say, we have some wave packet which is we could imagine a wave packet which is zero, which is non-zero. Well, let's say it's zero before this time, and then it's non-zero after this time. So then here on the left, yeah, let me get this straight. Let me first. So let me first do a toy model. So a toy model which consists of some signal transmission problem, which we start with some signal that is some function f in of time, right? Which will be 0 for times, will be equal to 0 for times bigger than 0, okay? And then we have some process that goes through some medium, and we expect the dynamics to be causal, so that f out should also be 0 for times bigger than 0. Okay, it should be 0 for times less than 0. So, sorry, I get all the signs incorrectly. Sorry, I have problems with C2 symmetries. So we have some signal, which initial signal, which turns out at time equal to 0, right? That's the f in. And the f out, so the outgoing signal has to continue being 0, and then, I mean, might have some delay or whatever, and can turn on later. Okay, so also have to have the same property. And if we Fourier transform this, then we imagine that the f out, let's say, is linearly related, and that the Fourier transforms are related to some sort of, we can call this an S matrix or e to the I phase shift delta of omega. We are assuming something like this, as you have when a particle goes through some medium with some index of refraction. Now, something that ensures this property is that this S of omega is analytic in the upper half plane. So in the upper half plane of omega, then if this function S is analytic and decreases in the upper half plane, then you can ensure this problem. And you can also show the opposite, that if you want this property to hold and the norm of these functions to be preserved and so on, or at least to be decreasing, you have to have this property of being S of omega being analytic in the upper half plane and decreasing towards the future. Okay, so now let's consider this situation, and we are going to make some analogy here. So where here x plus will be the analogous thing to time. So we want some signal which has not been turned on here, so it's 0 here, and then might be non-zero after this time. Okay. And so actually I was drawing this in the wrong way before. So what we want is that so this is where, this region is where the signal can be on, and so here there will be some time delay where, so if there is a time delay, the signal will come out here, but it's important that it will be 0 in this region. So actually, I apologize, but I was drawing this in the opposite direction. I told you I had some problems with some C2s. So the time delay case corresponds to this situation where it goes into, well, where this is, the signal arrives to a point. This is where the light rays would apply, and then this one comes in later. Okay, okay, very good. So that's the time delay situation. And if we want to enforce this, then we want that as a function of p lower plus, this function should be analytic in the upper half plane. And okay, so then this, whatever appears here in the exponent, should be, this whole thing should be analytic in the upper half plane. And that's, so this is the first order expression for the amplitude. What appears in the exponent is e to the I phase shift, and this I phase shift is ends up being something of the form minus I S 1 plus this alpha prime t, right? So we end up with something of this form. In, let's say, this is in general in string theory, but in any situation here we can get some A, and so this is something which here I put in the I in such a way that well, there are some properties that imply that as a function of S, when S goes into the imaginary direction, the function should be real. That's one reason for putting this I, so that when S is i's times something, this is a real quantity, and the whole thing decreases. But then, if you go back to the real axis, if this number is not less than 1, then you might get something that grows here, okay? Or vice versa, if it doesn't grow here, if A is bigger than 1, then it will grow somewhere in the upper half plane. Okay? So, in summary, what I'm trying to say here is that if you had a perturbative amplitude that grows faster than S, you would have some problems with causality. Okay? So causality in flat space also implies that this should be less than 1. So, inspired by this, we can say that that maybe lambda will always be less than the value we had for black holes, which was the maximal value. Okay? So this makes us conjecture that lambda is always less or equal than 2 pi over beta, or 2 pi t, and then, as I said, there was an h bar. So this is this would be a bound on the Lyapunov exponent, which in the classical limit it doesn't imply anything because h bar goes to 0, but in quantum mechanics is non-trivial, so there is some concrete bound. And it turns out that you can actually prove this bound by using general properties of quantum mechanics. So using the technique is somewhat similar to what Faulkner was discussing. So it uses taking these correlators and then doing some analytic continuation of the correlators in imaginary time and using some properties of the analyticity of the correlators in imaginary time. So it's very similar to the pictures that Faulkner was drawing for modular flows in general, but what they hold for, of course, the thermal ensemble. And then we need to assume that time order correlators actually thermalize, so the system thermalizes. And well, some general properties about n scaling, and with all, and also we, well, that fact that they thermalize is also the assumption the system is sufficiently chaotic. And with all these assumptions, you can prove this this bound. Okay. So this is the so-called chaos bound. I'm not giving you the proof. I've only given you a kind of motivation from causality in flat space, but I haven't given you the proof. Okay, so.
Does this bound apply only to holographic systems, or is it?
Oh yeah, no. This bound is supposed to apply to any system that obeys the assumptions, and the assumptions are pretty general. So we expect it to basically, yeah. Let me try to explain some point that is quite important for the existence of this bound. So the bound assumes, so we have this, for example, the OTC, so of the W. So this was 1 minus some correction 1 over n e to the lambda t, right? And it applies to this thing that is growing, okay? But in proving the bound, there is some. We also have to say that so even the time order one, so W B B W, right? So this could be like 1 plus some term, let's say alpha over n, which is not necessarily growing, but is some alpha. So the bound essentially holds when this term is bigger than this term. Okay? So this term is expected to grow because of this chaos business. This term is not, we don't expect it to grow, it's just a 1 over n correction to this story. But there are some systems where the bound might be violated because we might be in the regime where this is still small compared to this alpha. So an example of that is, imagine you have n electrons, n free electrons in a disordered medium, right? So then you can define some simple observables like the total momentum in the x or y direction and things like that. And then you find that in that system, when you compute this OTC, there is this piece here that grows faster than the bound. Okay? But in those same systems, so the behavior of this term there, so let me call it W of t, right? So it grows faster than the bound, but this never becomes very large. Okay? Never becomes larger than alpha. There is alpha, and then there is a region where it grows faster than the bound, but it does not become larger than this alpha. Okay? Especially in the region that is growing faster, is not bigger than what this alpha was. So that's an assumption in the derivation. Well, we had to assume that this term grew to something bigger than alpha, and then you can prove the bound. And so in that system, that assumption doesn't hold, and the conclusion also doesn't hold. But that is a system where the n electrons are free. So this term grows and saturates at some value, which is less than alpha, and but this never becomes a further one. So that single electron somehow, that single electron operator moves in space and does in a messy way, but never becomes many electrons. So that's the key difference. So we are assuming we have a system where the 1 over n correction is becoming larger than anything else, any of the other 1 over n corrections that remain finite, like this one. And that was a key assumption, and it will hold in chaotic systems. In many body chaotic systems, which are not integrable, we expect it to hold. So that was, I just gave you this example just to see in which case it doesn't hold.
I mean, a chaotic many-body system, because you mentioned
yes.
disordered electron.
Yeah, that is a single body system, and and this bound does not hold in that system. Yeah, simply because the bound holds when this term in the OTC becomes bigger than any other 1 over n correction that stays finite. Where this, because this is growing and eventually wants to become a further one, right? And so at some point it will become bigger than anything else, and that's when the regime in which the bound holds. I'm emphasizing that that's the generic expected behavior for a many-body system. So the systems where it doesn't hold, they have some integrability, are not really many-body systems. I mean, in that electron case, you have the many bodies and you have a Fermi energy and so on. So there is some aspect, many body aspect, that is really integrable. So it's not the same. Okay, so I'm almost done. Let me see. So one application of this bound is just to quantum field theory, and there you can. You can view the V and W, this could be the W of 0 could be an operator localized around this point, and the V of t could be an operator, so V of 0 could be an operator localized here, and then the time evolution could be the Rindler time evolution, right? So the boost around this, around the origin, and then so V of t would be an operator localized here. And then the situation is essentially the same as what we had in the general story, and actually the arguments for the bound also hold in this case. So in this case, it implies a bound now on the Regge behavior, and again says that that things behave like some. So the Regge behavior for amplitudes or these correlators is that with this big boost, the quantities behave like S to some J effective, and the idea is that so J lambda is this J effect. This is the same relation we had before for when we discussed amplitudes and the graviton and so on, and the string. Well, maybe I failed to mention that, but when something behaves like S to the here we had 1. So we discussed this amplitude for string theory, right? And then the relativistic, sometimes people express this in terms of the relativistic amplitude, which has a +1 here, right? And then this is defined to be some effective spin, sometimes called the Reche spin. And so the bound on lambda is a bound on the Reche spin, that saying that J effective is always less than 2. Okay. Okay, so that's thing. So, okay, so conclusions. So we saw that there is something interesting in the initial development of chaos in general systems, in the sense that we can have a general bound on Lyapunov exponents, and we got to this bound. So the bound is this bound, and we got to this bound by we were inspired to think about this bound by thinking about black holes and the connection to black holes, but the bound applies for any chaotic system. And so that's one point. Notice there is an H bar in this bound. There is no C in this bound. This has nothing to do with relativistic field theory. It applies in any system. And black hole saturated, so black holes you could be called as the most chaotic system in, well, it's among the most chaotic systems that we have in nature. The SYK model also saturates it. In black holes, this development of chaos has to do with a simple classical effect, which is this time delay when particles cross each other. I should have mentioned that this type of time delay is a version of the so-called Shapiro time delay. So it's one of the main tests of general relativity. It was found in the 60s. So Shapiro noticed that, so Einstein noticed that if you have the sun and you have light coming from a distant star, it will get bent by some angle. And Shapiro realized that if you look at the time travel that this light takes to go from this place to this place near the sun versus the time it would have taken if the sun wasn't there, well, it's also non-zero and measurable, and people have measured this effect. So it's a classic general relativity effect, and in the near horizon geometry, that sort of very simple classic general relativity effect gives rise to this chaos development. It's interpreted as chaos among the microstates of the black hole. I mean, it's interesting that, so chaos here has to do with some simple gravitational mode, which is this time delay. It's almost like a classical, well, it is a sort of classical effect in the, it's a tree-level diagram. That's the thing we computed. It's tree-level graviton exchange diagram. It's that single graviton is the mode responsible for this development of chaos. So something that looks like this chaos development will look like very complicated in the microscopic system, right? It had to do with these operators growing and so on, but it manifests into some simple mode. And I guess Hong Liu in his talk was emphasizing this fact and tried to get a general description for this, for the dynamics of this that would be valid not only in these gravity systems, but in more general systems. And I want to emphasize again that this is not the same as the chaos that is diagnosed by energy spacing, right? So this fact that the energy spacing is small, that has to do with much longer timescales. Those are interesting things, but all of these stories says nothing about that, okay? At least nothing so far understood. Okay, so I think I'm done, so thank you.
So naively, so this formula must maybe break down for some sufficiently low temperature. Because naively this formula said that zero temperature is not have chaos. And so what would be the temperature you expect it to break down?
Well, I mean, at sufficiently low temperatures, in some sense, we don't have chaos if we have just a few states, right? You have, let's say, you have the ground state, and you might excite to the next state, and you have some oscillatory behavior, right?
Yeah, but if you have a static system, even
Well, the problem.
in principle, inside the system,
Well, so if we. Well, if you have then you have a scale, you might have a scale invariant situation, then the temperature is still, well, an important point, so these excitations we are considering, right, the V and W, are simple excitations which increase the energy by order beta, right, by order the temperature. That's one of the things we're thinking about. So if you excite the system a lot, then you will be creating a new black hole. I mean, if you didn't have a black hole, you would be creating a new black hole, and then it becomes a little more complicated. It's not a small perturbation of the original system.
right, say for example, even in ABS,
Yes.
there might be some kind of, say, chaotic process in pure ABS. That may not include, say, the chaotic process in the boundary theory. But yeah, I'm just saying, even in the vacuum,
Yeah.
you excite a little bit, something going on without using the finite temperature. There might be some kind of the envelope exponent independent of the temperature, say at zero temperature.
Yeah, I mean, at zero temperature, some of these correlators develop power law form in time, so they don't display this exponential behavior. But I think I think your question is a little bit more depends on the setup that you consider. So if you consider a setup with a finite number of degrees of freedom and you go to zero temperature, then you are just focusing on the ground state and maybe the next excited level. So then it's clear you don't have this feature. Those would be exponentially small temperatures for the systems we are talking about here. Then you were asking about spatially extended systems. Yeah, there might be some other features related to that spatial extension. One point I didn't say anything about was in systems that have spatial extension, you can put the perturbation V at one point and the W at a different point, and then there is some kind of velocity that, yeah, maybe I'll just mention that because it has figured in some other talks. So then the basic formula is that there is some e to the lambda t minus Vx. So that's the generic behavior if we separate the V and X along some spatial direction. And people call this the butterfly velocity. Yeah, I should have mentioned that this effect is sometimes, this initial development of chaos is sometimes also called the butterfly effect. That you made a little perturbation and then it has a big effect later. Yeah.
Yes, you mentioned that the exponential, let's say the decay or growth is valid for very short times.
Yes.
But then almost 0 times, it starts as an exponential or has a different power law?
No. Yeah, it could have lots of transient things.
Before
before the exponential growth. Yeah. Yeah, because remember, well, I guess we can see that already in the black hole discussion. We had the scattering amplitude, right? And you can have scattering with various particles and, let's say, particles of spin 0, spin 1, and so on. Only when you get to large energies, you can have this this feature where the dominant thing is the graviton, and we have something that is growing in that case. So at small times, we can have some cancellations between different terms. And, yeah. Yes?
On an outside observer of a black hole,
Yeah.
how could you intuitively say that the black hole is the most chaotic object?
Well, you cannot do it if you cannot evolve the black hole backwards in time. So you have to have some way of being able to evolve the black hole backwards in time. So this is most concrete, I guess, if you had a system, let's say in the lab, that had a gravity dual, right? And that you can control very precisely, and then you can evolve it backwards and forwards. You would be able to say this. But yeah. There are systems that are most chaotic that do not have, well, the gravity dual is a little more tenuous, like the SYK model. And so that's a system which you could try to simulate in the lab and will have this behavior.
So in your first estimate of the amplitude, you write an I in front of the exponential term.
Ah, good. Yes.
Is that a typo or?
No, it's not a typo. I forgot to emphasize this point. So there is, in these systems of pure gravity, there is one small subtlety that. So the first term in the, actually the first term in the commutator, that I implies that the first term in the commutator is actually 0. So we have 0 times e to the lambda t, right? And then we have here some other terms which go like 1 over n squared. Okay. So for the gravity case, it's actually in the commutator we get the 0 at this level. But you can still define the lambda via the OTC through that formula. So that disappears once you have something that is not maximal chaos, and then you will have a non-zero term at that level. For the main message of the talk, this is a small detail, but well, you need to take into account for some things. Yeah. Mm-hmm.
Do you think all systems that are bound, saturated bound, would be like holographic or have a gravity dual, or is too much to ask?
Yeah, so that's what I thought. That's what I thought, and I think this is wrong. So. And somehow the SYK is a counterexample. So you have this SYK model, and it depends on what you mean by gravity dual. So if by gravity dual you mean a system that has local description in the bulk with standard local physics and so on, I think the answer is no. And it has to do with the fact that you even suppose another simple example, if you have a string theory with finite string tension in nearly ADS2 space, that is a system which we would say is not dual to gravity. So let's say we have ADS2 times S2 with tension of order the radius of curvature, or maybe slightly smaller than the radius of curvature. That's a system which we say, well, it's not quite gravity, right? Because there are big stringy corrections. So in that system, the Lyapunov exponent is still close to 1. So it's still 1. So how close to 1 it depends on how close to extremality you are. So if you're very close to extremality, then it will be very close to 1. So yeah. Yes.
Why at some point did you begin to speak about strings?
I didn't need to. So well, I could say that I spoke about strings because Hong Liu asked me a question, but I actually had prepared it before. So strings are were something that motivates the connection between weak and strong coupling. So I mean, in all these discussions of holography, one of the main advantages of strings is to be able to connect between weak and strong coupling. And so as you see that you turn on the stringy corrections, you start getting something that gets closer to the weakly coupled picture. Yeah. Yeah. Yeah.
What would be the other side?
Well, so if we had we could imagine a system that has some coupling constant g squared n, so some effective Toft coupling, right? And when this is large, we have some gravity picture, and then when this is small, we can have the stringy corrections. So for example, in ADS5 times S5, so you have some formula which says that this divided by radius of ADS to the fourth. Well, we had this that was controlling the corrections to the Lyapunov exponent, and this goes like 1 over square root of lambda, 1 over square root of that g squared n, right? So this is a quantity in the boundary theory side, right? That it's measuring how strong the coupling is, and this is the quantity that measured this correction to the Lyapunov exponent.
So my next question would be, in the n equals 4 superunions, you also have chaos.
Yeah, when lambda is very large, so when this is very large, so there are two lambdas. Unfortunately, this is sometimes also called lambda, but when this is very large, then we expect maximal chaos. Yeah. So maximal chaos is a property of any system that has an Einstein gravity dual. On the other hand, if G square n is very small, then we expect that the Lyapunov exponent, lambda Lyapunov, should be of order G square n. Okay, so it's very small compared to the temperature, well, times the temperature. When lambda is very large, so this is for G square n much less than 1, then for lambda Lyapunov should be 2 pi t for G square n much bigger than 1. Right? The same happens in the SYK model. So if you in the SYK model, so lambda, the Lyapunov lambda is equal to J for temperatures, very high temperatures, and lambda Lyapunov is equal to 2 pi temperature for temperatures much less than J. Okay. So this is the strong coupling region. So there the temperature plays the role. So J over T plays the role of the coupling. So this is the weak coupling regime, and this is the strong coupling regime. Yes.
So you motivated the discussion with these divergence of phase-space trajectories. So if I have a Laplacian system, which is chaotic, but the Laplacianism is not a classical limit, then do I still have in general this Lyapunov behavior, or?
Yeah. So the classical was just to make a connection to the classical notion of Lyapunov exponent. But yeah, all these systems, they don't necessarily have a classical limit. Like, for example, the SYK model doesn't have a classical limit, so it's just a quantum one. Well, in that sense, yeah. So yes. In all the systems, n, there is some expansion in 1 over n. And you might call that a classical limit, but exactly the nature of that classical limit in general is not very clearly understood. So, for example, Hong Liu was talking about some kind of hydrodynamic approximation, or yeah, there is this idea, but what is the general structure is not understood. Yes. Yes, well, the Heisenberg spin chain, I'm not sure what you mean by Heisenberg model, but the exact Heisenberg spin chain is integrable, so it will not have this behavior. But if you... Okay, yeah, then you should have this type of behavior. That's right.
So, are there more questions? Not less than 1 minute.